Hi, Assalamualaikum warahmatullahi wabarakatuh. Today we are going to continue chapter 7 Ionic Equilibria by learning lesson 40 regarding titrations. We should be able to describe the titration process, distinguish between the endpoint and equivalence point, perform calculations involving titration between strong acid and strong base, sketch and interpret the variation of pH against titre value for titrations between strong acid and strong base only. And then we're going to identify suitable indicators for acid-base titrations. Titration or titrimetry is a common laboratory method of quantitative chemical analysis. It's used to determine the unknown concentration of an identified analyte. Since volume measurements play a key role in titration, it's also known as volumetric analysis. In chemistry, there is one field, one part, a big part of it, called analytical chemistry. So this is just a beginning for that part of a chemistry world. For example, an application of this kind of analytical volumetry is be seen in car batteries that contains sulphuric acid. The concentration of acid must be maintained at 4.5 molars to ensure the proper operation of the battery. We have done acid-base titrations in the lab. What is titration? It's a procedure to determine the concentration of a solution using another solution of a known concentration, which is called standard solution. Look at the apparatus setup here. We've done this before. I'm sure you are familiar with this. In the burette, we insert the base, which is called titrant. And in the conical flask down there, we insert or we pour in the analyte. That solution is called analyte. There's a few terms that we need to know regarding acid-base titrations. Titration curve is a graph of pH versus volume of the titrant in the burette. The titrant is the solution that we add into the conical flask from the burette. The equivalence point is the point at which the number of mole of hydroxide ions added to a solution is equal to the number of mole of hydrogen ions originally present. And the endpoint is the point where the indicator changes color. So it's not necessarily a pH 7 neutral. What are indicators? It's a weak organic acid that is used to see the change in color over a range of pH values. Now, this is a famous titration experiment whereby before the endpoint, the color of the titrant is colorless. And then we do titration. Drop by drop, we're going to get the endpoint, and the color of the titrant now, when it reaches endpoint, is pale pink. It's quite difficult to get this color. You've been there before, because you will always miss the endpoint and get this. The pink, the red color is very strong there. That is past endpoint. There are actually 4 types of titration: strong acid and strong base on the left, strong acid and weak base on top, strong base and weak acid on the right, and the bottom one is weak acid and weak base. At pre-university level here, we're going to focus on strong acid and strong base. For the other 3, you're going to learn next year, inshallah. Now let's learn about acid-base titration curve. We know that titrant is a standardized solution with known concentration added from the burette. Titration curve is a graph of pH versus volume of titrant. That is what we're going to plot on the curve. Depending on the types of titration that we do, the endpoint or pH range and equivalence point would be different. For strong acid and strong base, the endpoint is quite big of a range, 3 to 10, and the equivalence point is 7. For titration of weak acid and strong base, the pH range is 7 to 11. Oh, that equivalence point is more than 7. Strong acid and weak base, the pH range is 3 to 7, and the equivalence point would be below than 7. A little bit of a note about acid-base titration here. You can see titrations involving only strong acid or strong bases are straightforward, meaning the equivalence pH is 7. But titrations involving weak acid or bases are complicated because the salt form will be hydrolyzed. Weak acid and strong base would have the pH at equivalent point more than 7, whereas strong acid and weak base would have the pH at equivalence less than 7. Now let's look at the titration of strong acid and strong base. This is the equation, the balance equation, sodium hydroxide aqueous form. React with hydrochloric acid in aqueous form to produce sodium chloride in aqueous form and water in liquid form. The net ionic equation would be H2O ionized to become H plus and OH minus. Shown to you here is a titration curve of the neutralization between sodium hydroxide and hydrogen chloride. And you can see the y-axis is pH, the x-axis is the volume of the sodium hydroxide. This is the titrant which is located in the burette. So at the beginning, we are adding 0, sodium hydroxide, 0 base. So the pH is 1. Look at the first dot there. And then, this is the first dot. We do titration. And then we measure the pH again. The pH now is higher because neutralization has happened. The H plus has decreased. Therefore, the pH increased. Now it's 1.18. The pH keeps getting higher and higher along the curve going up to the equivalent point at 7. Here, the sodium hydroxide added is 25 ml, as much as the quantity of HCl in the conical flask. What happened is the titration now is continued, and then we are still measuring the pH, and now it is a basic solution inside the conical flask. Finally, at the end, we got 12.5. Let's do example 7.18 in page 214. Consider the addition of 0.1 molar sodium hydroxide solution from a burette to an Erlenmeyer flask, conical flask, containing 25 ml of 0.1 molar HCl. calculate the pH of the solution before the titration begins. And after the addition of 24, 25, and 35 ml of 0.1 molar sodium hydroxide. I'm showing you this as a layout of the answers that you have to write in page 214. You need to use small handwriting and you need to add the titration curve on top. Firstly, for A, we have not done the titration yet, and in the conical flask, in the Erlenmeyer flask, there's only acid. HCl is a strong acid, therefore it ionizes completely. You can see the equation there. And given the concentration of the acid is 0.1 molar. So all you have to do is just make a negative logarithm of it, and you're going to get pH equals to 1. This is your first dot. Okay, now here is the ice table for the neutralization reaction of hydrochloric acid and sodium hydroxide. The first step that we need to do is find the number of mole for HCl. 25 is the volume, multiply by the molarity 0.1, divide by 1,000 because this is calculated in liters. We got 2.5 times 10 to the power of negative 3. Sodium hydroxide has the number of mole 2.4 times 10 to the power of negative 3. Calculate using the same method. Okay. Then we look at the change. We're going to use all of the OH minus supplied by sodium hydroxide, which is 2.4 times 10 to the power of negative 3. So the 2.5 will be deducted with 2.4, making it to only have 1 times 10 to the power of negative 4 mole. This is the final number of mole for HCl. So we find the new concentration of HCl. We have to find the total volume. The total volume is 25 plus 24. Divide by 1,000. We got 49 times 10 to the power of negative 3. So the concentration now is 2.04 times 10 to the power of negative 3 molar. And the pH solution now is calculated from the amount of hydrochloric acid left after partial neutralization. This is not yet the endpoint. So we use negative logarithm of H plus and we got 2.69. For C, what happens if we add the same amount of sodium hydroxide, 25 ml? We will notice that there is no H plus left and there is no OH minus left. We got 0.05 molar of sodium chloride as a product, as shown in the slide. The calculation involves a complete neutralization reaction. The salt does not undergo hydrolysis, so at equivalent point, the concentration of H plus is equal to the concentration of OH minus, therefore, the pH is 7. Finally, for D, what happens if we add the volume of sodium hydroxide more than the volume of HCl in the conical flask? 35 ml multiply by the molarity 0.1 divide by 1,000, that is the number of mole for sodium hydroxide there. And we notice that we are going to have an extra sodium hydroxide at the final stage of the titration. So we calculate the molarity. Notice that the total volume of the solution now is 60 times 10 to the power negative 3 because we add 25 and 35. Oops, sorry. we got 60 over 1,000, making 8 liters, so 10 to the power of -3. The final concentration now is 0.017 molar. So basically, we are going to find the POH first, which is 1.77, and then subtract it from 14, and we got pH 12.23. So what happens here is we want you to plot the graph. We want you to sketch the graph. The graph is going to be pH on the y-axis, the volume of the sodium hydroxide on the x-axis, and you're going to have 4 plotted points here. The first one having pH 2.69, the second one 7, the third one 12.23. What was the other one? Maybe the first point when the titration has not begun. The sole pH of acid 0.1 molar, so that is pH 1, pH 2.69, pH 5, and now pH 12.23. You have to be able to sketch the graph, and the curve would be distorted S. All right. Okay, I'm going to show you how to draw the titration curve. If you have a graph paper, it would be very good. So I'm drawing the axis. The y-axis is the pH, and then the x-axis would be the volume of sodium hydroxide in ml. Okay, we have 4 points. The first one is 1, 2.69, 7, and 12.23. So before we do the titration at 0 ml, the pH is 1. So this is the first dot. And then when we do titration at 25 ml, not 25, 24 ml, we got the pH 2.69, so it's around here. Okay, and then the next point is at the equivalent point, which is 7. So this is 3, 4, 5, 6, 7. This is 7. So the equivalent for 7 is important. We draw this very clearly, like this. This is the equivalent point whereby the pH is equals to 7, and then at 35 we have 8, 9, 10, 11, 12, 12.23. That would be here somehow. Okay, that is 35. Right, how are we going to draw the curve? The curve is a distorted S. So it looks like an S, but it is distorted. So the first thing that you do is the vertical line in the middle here, going across the equilibrium point, and then the curve there. This one also going to the curve over here. So this is how you draw the titration curve. Now please do practice 7.5 and try to plot the titration curve on a graph paper. This is a very good exercise for you. Let's look at acid-base indicators now. What are indicators? They are substances that have distinctly different colors in acidic and basic media. An indicator is usually coming from a weak organic acid or base that has distinctly different colors in its non-ionized and ionized form. The endpoint of a titration occurs when the indicator changes color. Not all indicators change color at the same pH, so we need to choose which one is suitable for the nature of our titration. The choice of indicator for a particular titration depends on the nature of the acid and base used in titration. By choosing the proper indicator for a titration, we can use the endpoint to determine the equivalence point. There are two types of indicators in acid and base titrations: weak acids and weak base. Here are some common acid-base indicators that we used in the lab. Example, thymol blue here. It will change color from red to yellow, and the pH range is 1.2 to 2.8. Let's look at the famous ones, the most used, phenolphthalein. In acidic, it is colorless, but in basic, it's pink, 8.3 to 10. The pH range is defined as the range over which the indicator changes from the acid color to the base color. So we need to be able to find the pH range that have the end point that we want. Look at how colorful the indicators are, subhanallah. Bromothymol blue changes from yellow to blue. Litmus, we are familiar with this. Red to blue. Methyl orange and methyl red, yellow to red. Phenolphthalein, white to pale pink. Phenol red, yellow to red, and thymol blue is having 3 colors. So beautiful. Red and acidic, yellow in the middle, and blue at the basic condition. Now, how do we choose a suitable indicator? We need to choose an indicator which the endpoint pH range lies on the steep part of the titration curve. This choice ensures that the pH at the equivalent point will fall within the range over which the indicator changes color. Now let's look at table 7.5. Listed there is the endpoint and the pH range, and the suitable indicator that is suggested for the type of titration. You can see the table in page 216. For strong acid and strong base, we need the pH range from 3 to 10. Basically, we can use any indicator. But for weak acid and strong base, 7-11, we can use phenolphthalein and thymol blue. For strong acid and weak base, 3 to 7, we can use methyl orange and methyl red. Here are suitable indicators suggested for strong acid and strong base titration according to the titration curve. You can see the litmus is used red to blue, methyl red, red to yellow, phenolphthalein, and bromothymol blue. Here is more suggestion on what indicator to use according to the pH scale. So they are alizarin yellow or thymolphthalein, phenolphthalein, thymol blue, phenol red, bromothymol blue, chlorophenol red, bromcrystal green, methyl orange, bromphenol blue, thymol blue, and methyl violet. All of these can be used according to the pH range, the endpoint where the indicator will change color from acid to base. A lot of students must be wondering, Madam, Do we need to memorize the table? How do we know the pH range? And here we show you the example of a question. What is the color of the solution when 3 drops of below indicators are added separately to water? The pH range is going to be given in the question. All you have to do is decide which color is going to appear. So for pH 7, the color for phenolphthalein is going to be colorless. For methyl orange, it's going to be yellow because red is the acidic range. 7 is way past the yellow part, so it's yellow. For bromothymol blue, 7 is blue. For phenol red, 7 is basically red. Another question. The pH range and the color change for 3 indicator XYZ is shown in the table below. What is the color of the solution when a few drops of above indicators are added separately to a buffer solution whose pH is 6.52? For 6.52, X is going to be yellow. So it's going to be C, D, or E. For 6.52, Y is going to be yellow. E. And Z, 6.52 is going to be colorless. The answer is E. Next question. Which indicators would you use for a titration of the nitric acid with potassium hydroxide? This is a weak acid titrated with strong base. So at equivalent point, we're going to have conjugate base of weak acid. So it is going to be more than 7. Which indicator which is suitable? Look at the pH range and we must find the ones that are basic. So we can use cresol red and phenolphthalein. We have come to the end of lesson 40. Thank you very much for listening and watching. We will see you again for the last time this semester soon, inshallah. Assalamualaikum warahmatullahi wabarakatuh. Happy studying for finals.